Good morning, friends. It's my great pleasure and honor to speak in a symposium that pays tribute to William Eberhard and Mary Jane West-Eberhard. Mary Jane and Bill have been my career-long heroes and role models. They have certainly been the inspiration for me to study the behavior of the Indian paper wasp, and to do it in what I call the tradition of the Eberhards, which is captured nicely in the subtitle of the symposium, using detailed observations of behavior, both for generating questions and for answering them. But let me begin by saying a few words of how Mary Jane and Bill came to be my heroes. It was my great fortune that the world's most famous wasp researcher, Mary Jane West-Eberhard, came to India to participate in a seminar on evolution of social behavior, which we had organized at the picturesque hill station of Mahabaleshwar near the city of Pune in Maharashtra in India in 1979. A galaxy of the world's greatest experts on social behavior, including John Maynard Smith, William Eberhard, John Hurrell Crook, Robert L. Trivers, and John F. Eisenberg participated in the seminar apart from Mary Jane herself. But for me, Mary Jane Eberhard was very special. For one thing, she was a wasp expert. Some of us call her the wasp queen. She's also one of the kindest and most altruistic scientists I've had the privilege of knowing. She came to Bangalore and stayed on for a few weeks, and among many other things, she taught me how to mark the wasps. She also left behind her box of Testor's enamel paints that she always carried with her when she traveled. She also left behind several thousand rupees that she had saved from her per diem as a startup grant for my research on wasp behavior. I set aside that amount, calling it the Mary Jane Fund, and it was more than sufficient to finance my low-cost research for some years. It even afforded me the luxury of traveling daily in an auto rickshaw to watch Rhopalidia colonies in Cubbon Park in the city of Bangalore. Just a brief introduction to Rhopalidia marginata, this beautiful wasp that we fondly call the Indian paper wasp. Rhopalidia marginata is a tropical primitively eusocial social wasp, which means that there is no morphological caste differentiation. Queens and workers look alike, and you can only tell the queen apart from the workers if you see her actually laying an egg. Because these wasps live in a tropical climate, they have a perennial, aseasonal, indeterminate colony cycle, which means colonies are founded any time of the year, they can be abandoned any time of the year, and there is no particular fixed duration for the colony cycle. That is from the beginning of a colony to end of a colony. It can last a few days or it can last a few years. And the colonies are strictly monogynous, meaning that at any given time, there's only one queen and the rest of the wasps are workers, and they refrain from egg laying and they work for the welfare of the colony. As I said, these wasps live in India, and it is our fortune that they like to live around human habitation. So we can go and study them wherever they have built their nests. This could be in the gardens, on the eaves of buildings, on the windows, and they even come voluntarily and build their nests in our lab. But it is also equally easy to remove the nests along with the adults from their place of natural initiation and put them in laboratory cages, and it is possible to house a large number of cages in our lab, which we call the Westpiary. As I said, this is a series of questions and answers, and that's how we conduct our research. So I will use this opportunity to illustrate how making behavioral observations to generate questions and answers can be worked out in this Indian paper wasp. So let me begin by the first question, which I asked very, very early in my career. Because this is a primitively eusocial species and there is no morphological differentiation between queens and workers, I was curious, how does the queen behave as compared to her workers? Because she doesn't look different, at least she should behave differently. observation suggested that she does not behave qualitatively in any way different from the workers. She seems to do all the things that the workers do, at least she can, and only thing is she lays eggs, which the workers do not. So the difference in the behavior of the queen and the workers must be quantitative. And in order to test this possibility, I constructed time activity budgets for all the marked wasps in a colony. In other words, I measured the amount of time each wasp spent in each behavior, and using this data and subjecting this data to multivariate statistical analysis and followed by cluster analysis. So in this case, principal components analysis followed by cluster analysis revealed, most interestingly, that the wasps in every colony can be classified into three rather distinct behavioral clusters. We call these behavioral castes because there are no morphological castes in this species. Even the queen and worker are not morphologically different. And based on the major behavior of each of these clusters, we named them as sitters, fighters, and foragers. So the answer to this question is that the queen behaves differently. Now, how did we know that? When we did this analysis, we deliberately did not identify the queen. We did not treat the queen in any different way. If she doesn't look different, why should we treat her differently? In other words, I did not tell my computer who the queen was. The advantage of this is at the end of the analysis, I could come back and ask post facto, where is the queen? Is she a sitter? Is she a fighter? Or is she a forager? Now, earlier work on other species suggested that the queen should be a fighter, because in such primitively social species, it was known at that time that queens use physical aggression to control their workers, both the worker reproduction and the worker activities. So we expected the queens to be fighters, but to our great surprise and to our great delight, our queen was not a fighter. In colony after colony, we found that the queens were sitters. So the simple answer to the question is the queen in Rhopalidia marginata is a non-aggressive, non-interactive, meek and docile sitter. Now, as it always happens, when we answer such a question, we have to take this question with a pinch of salt. We have to put it on hold because it raises other questions. And unless we answer those questions, we don't have confidence in this question. So the queen is a non-aggressive, non-interactive, meek and docile sitter. Let's put that on hold. Let's accept that tentatively and see whether we can justify this answer by asking future questions and future answers. For example, this answer immediately raises a perplexing question. If the queen is such a meek and docile sitter, how did she become a queen in the first place? Why do the workers accept her and respect her? Indeed, they respect her because they never attempt to lay eggs. They never develop their ovaries and lay eggs in her presence. So how did she become a queen in the first place? Now, in order to answer this question, we had to do an experiment and then do the observation. And the experiment consisted simply of creating a situation where we can actually observe the process by which an individual becomes a queen. And that was a simple experiment. It lasted 3 days. On day 1, we observed a natural colony, the queen and the workers in their natural setting, meaning we constructed time activity budgets for all the wasps. On day 2, we experimentally removed the queen and observed the rest of the colony without the queen. And on day 3, we actually returned the queen back to the colony and we once again observed all the individuals, the queen and the workers, to see their behavior. Now, this resulted in a remarkable observation. It turns out that Rhopalidia marginata is a reasonably peaceful society. There are low levels of dominant subordinate interactions between the workers, but by no means is it a hyper-aggressive society. However, as soon as you remove the queen, one individual became hyper-aggressive. In fact, the levels of dominant subordinate interactions in the colonies, as soon as we removed the queen, went up several-fold. 2-fold, 3-fold. We have even seen 30 to 40-fold increases in the dominant subordinate interactions, in the rates of these interactions per hour in the colony as soon as we remove the colony. What is even more interesting is that all of this new aggression is shown by one of the workers. And this worker then stops being aggressive if we return the queen. So the data looks like this. On day one, almost nobody is aggressive. On day two, one individual shoots up her aggression and she will drop her aggression on day three when we return the queen. And if you wait for another day, her aggression will become no different from what it was in the presence of the queen on day one. Now we know that if we do not return the queen, this hyper-aggressive individual will go on to become the next queen in about a week's time. So we call her the potential queen. So the answer to our question is potential queens begin their careers as very aggressive individuals and only later become meek and docile. So how does an individual become a queen in the first place? If she is a meek and docile sitter, the answer is when she becomes a queen, she is not a meek and docile sitter, she is a hyper-aggressive individual. Now, so this gives us more confidence in the first answer, but we have to put this answer on hold because if indeed she is aggressive only for a week, whereas her tenure may last for several months to even a year, then how does a meek and docile queen inhibit worker reproduction throughout her career? Now, in order to answer this question, we had to do a different experiment. We hypothesized that the Rhopalia marginata queen, even though she belongs to a primitively eusocial species, might actually be producing pheromones to control her workers or to control her worker reproduction. So in order to test this possibility, we did a different kind of experiment, but always followed by observations. Here what we did was we brought the nest to the laboratory. We housed it in a cage. And on day one, we observed all the wasps, including the queen and the worker. On day two, instead of removing the queen, we cut the nest in half and dividing the brood roughly equally on either side and inserted a wire mesh screen between the two halves of the nest. The purpose of the wire mesh screen was to prevent the wasp from going across, but allow any volatile chemicals that might go across if the queen pheromone, in fact, is a volatile substance. Now, after we inserted the wire mesh, we reintroduced the wasp one by one into the cage. So basically what we did was we divided the workers, one half on one side, another half on the other side randomly. We would pick up a wasp, toss a coin and say heads you go left and tails you go right. At the end of all the workers, we took the queen and treated her in exactly the same way because she looks like everybody else. We said heads you go left, tails you go right. So we now had one half of the colony on the queen right side and the other half as the queen left side. And we observed both of these sides, the behavior of wasps on both these sides simultaneously. On day three, the equivalent of returning the queen, we moved the queen from yesterday's queen right side to the queen left side. So now the queen right and queen left sides will interchange, and again we observed both sides. Now, our predictions for this somewhat elaborate experimental design were as follows. If the queen pheromone is volatile, both nest fragments should behave like queen right colonies, because the volatile substance would go through and the workers on the opposite side, on the queenless side, would be able to recognize, would be able to smell and recognize the presence of the queen. So nothing special should happen. However, if the queen pheromone is non-volatile, then the queenless fragment should behave like a queenless colony because they no longer can sense the queen, they no longer have the queen, and therefore there should be a hyper-aggressive individual. Now, this particular experimental design has turned out to be very useful. We have used it on many other occasions, and I will have opportunity to illustrate at least one more question answer with this design. But even at the time this slide was made, we had already performed this experiment 24 times. And in all 24 experiments, prediction 2 was upheld. In other words, the pheromone is non-volatile. So this is what the data looks like. On day 1, nobody is aggressive. On day 2, one individual becomes hyper-aggressive on the queenless side. When we bring the queen to her side on day 3, she drops her aggression, and another individual, which was not showing aggression yesterday because the queen was on her side, now shows aggression because the queen is not on her side. And of course, we don't know who this PQ1 and PQ2 were on day 1. Post facto, we can identify them because the wasps are all marked, and we showed that neither the queen nor PQ1 nor PQ2 showed any significant amount of aggression on day 1, but systematically they increased and decreased their aggression as predicted. In other words, our marginata queens appear to use non-volatile pheromones to inhibit worker reproduction, or at least to announce their presence and their fertility to the workers. Now, again, as you can see, this gives us confidence in our previous question. answer to our previous question, but we have to put this on hold in order to ask and answer other questions. This is how research proceeds in my group. We love to watch the wasp. As we watch the wasp, some questions arise. We try to observe, do experiments, set up a design, a study, answer that question, put that question on hold, and try to answer another question, one or two or more questions that arise from the answer to the first question. So the next question that arises, if in fact the queen is using a non-volatile pheromone, how do the workers perceive the queen pheromone? Because it's not volatile anymore. Even in a normal natural colony where there is no wire mesh separating the workers and the queen, how do the workers receive? Now, we actually spent a lot of time answering this question, but in the interest of time, I'll only give you the answers. In this case, I won't give you the details of the experiments. We proposed that workers receive the queen pheromone through direct physical interaction with the queen, and we showed that this is not true. We proposed that workers receive the queen pheromone through indirect physical interaction by relay from other workers, and we found that this is not true either. And then we found, so we computed the rates of physical interaction between all pairs of wasps. We then computed the shortest path of information flow from the queen to the potential queen, both directly as well as relayed through workers. And this is how we found that the PQ detected the presence of the queen too rapidly, that is in less than 30 minutes, or the absence of the queen too rapidly in less than 30 minutes for information to have reached her through physical interaction. Therefore, our answer, by making further observations, we showed that the queen actually applies her pheromone to the nest by rubbing her abdomen on the nest surface, and the workers then get it by smelling the nest, not directly by interacting with the queen. The next question is, can we really predict the identity of the queen in the presence of the queen? As soon as we remove the queen, one individual becomes hyper-aggressive. Now, who is this individual? Can we predict this individual? Again, we spent a lot of time trying to answer this question, in this case, without much success. In fact, to give you an example of the kind of things we did, we studied the behavior of all the individuals. And for example, in the principal component space here, you can see that the queens and the potential queens and the workers are all mixed up. Only the queens stand out. In other words, no, we cannot predict the identity of the potential queen in the presence of the queen. The potential queen appears not to be unique by any criterion, not her dominance rank, not any other behavior, nor even her ovarian rank. At this stage, we said, okay, we cannot predict, but do the wasps know who their potential queen is? Now, in order to answer this question, we have to ask it in a slightly more scientific way. And the scientific way of asking this question is it possible that there is a hair designate, even though we cannot identify her? And do the other wasps know who this hair designate is? Now, in order to answer this question, we conducted a very different kind of experiment, but once again, using the same strategy of cutting a nest in half and inserting a wire mesh. Now, here we said, we use a different strategy of experimental design. We said, let us assume that there is a hair designate. Let us assume that all the wasps know who she is. Now we do an experiment. We subject the wasp to an artificial situation and we predict how they should behave if indeed there is a hair designate and if indeed all the wasps know who she is. So I will illustrate this very briefly using an animation. So imagine that this is the nest. So there's one half with the queen, another half without the queen. And by chance itself, by chance alone, it may so happen that the hair designate is on the opposite side of the queen. In such a case, she of course will become hyper-aggressive. So let's call her the potential queen 1. But if she is the true hair designate, she should not just be accepted as a queen on this side, but she should be acceptable to the whole colony. To test whether that is true, we interchange the position of the queen and the PQ1, and we should find that the PQ1 is accepted by the wasp on this side also, and she is not challenged. Move her back, she should not be challenged anywhere. Then she is indeed the true hair designate, and all the wasps know who she is and that she is their next queen. However, in about half the experiment, the potential queen might land up because we distributed them randomly on the queen's right side, which means she cannot show any aggression because the queen is right there on her side, rubbing her abdomen on the nest, rubbing her pheromone on the nest. Now, what would happen in such a situation, we expect, is that on the opposite side, on the queenless side, even though there is no heir designate, no queen, no heir designate, but the best individual should then become a potential queen. Let us call her PQ1. But she is a potential queen only for her side, not for the whole colony. And therefore, when we interchange the queen and PQ1, there should be a problem. That is, the PQ1 now comes face to face with the true heir designate, and she should no longer be aggressive. The heir designate, the true heir designate, should become a hyper-aggressive individual. Let us call her PQ2. But that's not the end of the story. The acid test for PQ2 is when we move her to the opposite side, she should also be acceptable to the opposite side. In other words, our predictions are that PQ1 should be unacceptable to the opposite side in about half the experiments, and a second potential queen should emerge on that side. And the potential queen number 2 should be acceptable to both sides. No PQ3 should emerge after the PQ2 was removed in the opposite side. That is, if you cut the nest in half, there should be only 2 potential queens, not 3 or more. Now, this is a beautiful design, but a very tedious set of experiment. But the student who was passionate about this question spent a lot of time doing the experiment, and she did this experiment successfully 8 times. In 3 of these experiments, the first individual to become hyperaggressive was unchallenged on both sides. This corresponds to the situation where she might actually be the heir designate by chance being found on the queenless side at the beginning of the experiment. But in the remaining 5 experiments, the first individual to become hyperaggressive had to lose her aggression, and a second individual became. In other words, the PQ2 emerged, a second potential queen emerged in about 50% of the experiments. No PQ3 emerged in any of the experiments. Both predictions were upheld, suggesting that there is indeed a heir designate. But what is our confidence that the wasps actually know who this heir designate? This confidence doesn't come from statistical analysis, but by the simple observation that it is remarkable that the potential queen 2 was never challenged. She did not receive a single act of aggression by the PQ1 or by any of the workers, either when she emerged in the presence of the PQ1 or when she was moved to the opposite. In fact, nobody challenged her. Even the PQ1 did not challenge her. That's why we believe that the heir designate was obviously known and acceptable to all the wasps, including to the PQ1. Now, this was a very satisfying result, but we really got a kick when we were able to publish a paper with the title, "We know that the wasps know," because there are cryptic successors to the queen in Rhopalidia marginata. All along we had been saying we don't know who the new queen is, but now we could say we don't know, but we know that the wasps know. Now this leads to another question which the next student asked, how do you know? So the answer is there is a heir designate, even though we cannot identify her in the presence of the queen, and the wasps seem to know who she is. A question again arises from this. Is there just one heir designate, or is there a queue of heir designates patiently awaiting their turn? Now, to do this experiment, answer this question, yet another experiment. Take a normal colony, observe all the wasps, identify the queen, remove the queen, identify PQ1, and then remove her to see what happens. And when you do that, indeed, we can show that there are a series of potential queens. On day 1, in the presence of the queen, nobody shows aggression. Remove the queen, one and only one worker becomes hyper-aggressive. Remove her, of the remaining wasps, one and only one becomes hyper-aggressive. Remove her, of the remaining wasps, one and only one. So we were able to show that there are at least 5 such individuals which are heir designates waiting for their turn, but nobody challenges them when they become aggressive at the time of their turn. And these individuals are not challenged, as seen by the blue bars here, which are essentially 0. This is the rate of dominance received by them. In other words, there is a long reproductive queue of at least 5 potential queens, but perhaps the queue is even longer. Maybe all individuals are in fact lining up in the queue. This meant we should re-examine the question of whether we can predict the potential queen, because the wasps also seem to know, and can we? So we further studied this phenomenon. In fact, one of my students persisted with this question and said, can we really identify the potential queen? She collaborated with Professor Noah Pinter-Wollman of the University of California, Los Angeles, and used multivariate network analysis to see whether we could actually predict the potential queen in the presence of the old queen before removing the old queen. So we have now used the novel analytic approach of multi-layer network that combines multiple social situations into a single mathematical object. In the multi-layer network analysis, the number of individuals that the PQ interacted with was significantly higher than 95% of the values obtained in the randomized scenarios. But when examining each situation separately, there was no such pattern. And the situations we used were, in this case, were aggression, prophylaxis, solid food exchange, and spatial overlap. And only when in the multi-layer analysis, we could see that the PQ stands out from the other. So we can probably identify the new queen after all by using such a method. But this, as you can see, raises a very important question, a new puzzling question. How do the rest of the workers recognize the PQ without the aid of multi-layer network analysis? As far as we know, they don't perform multi-layer network analysis. But how do they actually recognize the queen? Now, only future work will tell how this happens, because at present we do not know. I take you to another question. We know that some wasps leave their parent nest and start new nests. Which are the wasps which leave their natal nest and found new nests? Now, in order to answer this question, actually we had some difficulty. For a long time, this phenomenon of nest foundation had been very hard for us to study. In the field, we see wasps leaving their nests, but we do not know where they go. We also see nests being founded, but we don't know where the wasps came from. And in the lab cages that we normally use, which I showed you in the West-Eberhard, there was not enough space, and we rarely observed wasps leave their nest and start new nests. Probably there wasn't enough space. So we simply built very large so-called walk-in cages where I could put the nest as well as a student inside the cage, and observations could be made. Here there was enough space, and indeed we were able to observe wasps leaving their natal nest and starting new nests. So even in the first experiment in the walk-in cages, we observed 29 new nest initiations from 9 parent nests, 9 single foundress nests, and 20 multiple foundress nests. Now, all that we did was keep a diary of the happenings in these walk-in cages. What happened every day? What happened in the old nest? What happened in the new nest? Who left the nest? Who joined? Who returned? And just by keeping a diary of our behavioral observations, we were able to observe many unusual behaviors which we had not seen before. Wasps congregated outside their parent nest and showed dominant-subordinate interactions before initiating new multiple foundress nests. The most dominant wasps of such aggregations always became the queens in multiple foundress nests. Others became co-foundresses or did not join any new nest. Solitary foundresses and future queens of multiple foundress nests engage in self-feeding behavior outside their parent nest, a behavior which we had not seen so far. So the answer to this question is behaviorally dominant and well-fed wasps tend to leave their natal nest to found new nests either singly or joint. They prepare for this future by altering their behavior both on the nest and off the nest. They feed well, they show aggression, and they prepare for this new life. Therefore, now we could test the hypothesis that wasps are not pre-programmed robots. Modeling their evolution as a competition between bearers of alternate alleles with fixed behaviors can be misleading. Clearly, the wasp must be making and changing decisions continuously based on updating their information about their internal state and the state of the external world. This gives us hope that we can change their behavior by changing their internal state or the external world around them. If so, can we make the wasp more or less altruistic at our will? Can we alter their relative dependence on direct versus indirect fitness? So our question is, can we make the wasp more or less selfish at our will? Our experiment to test this possibility was as follows. We transplanted 12 R. marginata nests into the West-Eberhard, into these large walk-in cages, each one inside a separate walk-in cage. We randomly assigned the nest either to a control group or a test group. There were 6 control and 6 test nests. We provided ad libitum food to all the nests. Corsera cephalonica larvae is what we feed them. Also water and honey every day. So ad libitum food was given to all the nests. However, in the test nest, in addition to the ad libitum food, we hand fed the 6 nests twice a day. So we would offer food with a forceps to every individual wasp And during each hand feeding session, we offered larvae to each adult female present on the nest until the time they did not accept any more larvae. And therefore, we tested whether indeed this had increased food intake by the wasp. We were able to show that there was a statistically significant 1.7-fold increase in the food intake of the wasp, per capita food intake of the wasp in the test nest compared to the control nest. Now we could compare the altruistic and selfish behavior. So we were able to show that there was a 3-fold increase in the nest foundations per day. So the wasps had much higher probability of leaving their parent nest and starting their own nest in the well-fed nest compared to the control nest. Even in terms of ousting the original queen and becoming replacement queens in the original nest, the queen turnovers per nest per day actually increased 12-fold in the well-fed nest compared to the control nest. Now, we could also treat the feeding rate as a continuous variable, and we were able to show that there was statistically significant positive correlation between feeding rate and nest foundation as well as queen turnover. So our answer to the question is yes, we can make the wasp more selfish. We can make them have a higher probability of leaving their natural nest and founding new nest and getting more direct fitness. This gives us confidence that we have some understanding of the factors that make some wasps so altruistic and some wasps selfish. So this, of course, raises another new puzzling question. Why do the wasps not feed enough on their own and become more selfish even in the control nest, even in natural colonies? We provided them ad libitum food. This is a really puzzling question, and again, only future will tell. So this saga of questions and answers continues in our group, as it always should, because every answer leads to a new question. Now, I want to end by saying that I have tried to summarize and convey these in many forms. Very early, many years ago, I wrote a book called Survival Strategies, in which I tried to place our research in the larger context of the field of behavioral ecology, sociobiology, and evolutionary biology. I've also written a monograph on social biology of Rhopalidia, in which some of the early work is described. Of course, this book is already quite old, and a new book is due. I'm now starting to work on a second book on Rhopalidia. But I've also written more recently another book called Experiments in Animal Behavior, Cutting Edge Research at Trifling Cost. My goal in this book is to show that you can actually do cutting edge research with almost no cost. I will read out a few sentences from the preface of the book to give you an idea about it. This book contains 16 chapters, 5 on Rhopalidia marginata, but also on other species picked up from the literature. I'll read a few sentences. 21st century industrialized science is wonderful and welcome, but it has one avoidable downside. It relegates the vast majority of humanity to the role of an awestruck audience, constraining them to be consumers of knowledge without the hope of becoming knowledge producers. But this need not be the case. Alongside the industrialized science, there is continuing room and need for simple, low-cost, where ideas trump technology kind of science that is open to all, young and old, rich and poor, professional and amateur. Simple experiments propelled by ideas rather than technology and large grants can be both the fountainhead as well as the cutting edge of scientific research well into the 21st century and beyond. The upside of this brand of science is that it can make knowledge production an inclusive and democratic enterprise and contribute towards constructing a more egalitarian world. My aim in this book is therefore to make cutting-edge research at trifling cost an attractive option for large numbers of scientists and convert an even larger number of aspiring scientists into practicing scientists. I've chosen the field of animal behavior to illustrate the beauty and power of simple low-cost experiments because this is my area of expertise. I have no doubt that similar endeavors can be made in many other areas of natural science within and outside of biology. Finally, I try to take my research to the general public. Every month, I write a column, and my column is called More Fun Than Fun. And every week, every month, I take a topic in behavior, mostly in animal behavior, behavioral ecology, evolutionary biology, and both the book and this column are freely available at the sites given here. And I want to end by thanking my very large number of my students. As I said, I do low-cost research. I have some money given by various agencies of the government of India, which I use largely to pay salaries of students, because I need very little equipment. But these students are the backbone of the laboratory. They ask questions, they challenge, and I have always a great pleasure in working with these students rather than with instruments. When people ask me, where is your sophisticated instruments laboratory? I tell people that the heads of these students are all my sophisticated instruments, which I use to answer this. And there is great fun in doing this kind of thing. And I'm delighted to have had the opportunity to tell you a little bit about the kind of work we do. Once again, I want to pay my tribute to Mary Jane and Bill Eberhard for inspiring me to do this kind of research. Thank you very much.